So up next, we have the preview for the domain-specific languages session, and we're hearing from John Wickerson from Imperial College. Take it away.
Thank you, Sam. Okay, so I'm going to give an introduction to the domain-specific languages session coming later this afternoon. I'm going to try not to summarize the papers that are going to be presented, because the last thing I want is you thinking that you don't actually need to attend that session anymore. Rather, I want to try and introduce the papers a little bit, give a little bit of background, a little bit of context about where these papers come in. So the papers are all about DSLs, domain-specific languages, so any language that's really not a general-purpose language, rather a language that is designed to be particularly good at solving problems in a particular domain. And all of these 4 papers in this session, they either propose a new DSL or they study an existing DSL. Other than that, there's not actually very much in common between these 4 papers. Okay, so the first paper is called EasyBC. It's a new DSL for defining block ciphers. So a cipher, that's a method for encrypting data. It takes an encryption key, some data, mashes those 2 things together, and it produces some encrypted output. It's called a block cipher because it processes the data in fixed-sized blocks. That's as opposed to a stream cipher that encrypts data 1 bit at a time. People like to attack block ciphers. One kind of attack is called a differential cryptanalysis. And how this works is that an attacker chooses 2 inputs that have a specific difference between them. And they see what the effect is on the difference between the 2 corresponding outputs. It's a probabilistic attack, which means if you observe certain output differences slightly more often than others, then certain keys may become slightly more likely than others. And this information may be enough to drastically reduce the amount of time needed to work out the actual key. So nowadays, if you propose a new block cipher, you have to prove that it is resistant to differential cryptanalysis. And that means you need to be able to do a probabilistic analysis of your block cipher. Now, if your block cipher is programmed in this new DSL that's proposed in this paper called EasyBC, then you can use a procedure that's also supplied with the paper to translate that block cipher into mixed integer linear programming constraints. You can solve those constraints, and that will give you a good approximation of how resistant your block cipher is. Okay, so that's paper 1. Paper 2 is called a core calculus for documents. So this is studying DSLs for producing documents. Now, there are many examples of this. The simplest possible case is just a static text file or a quoted string in any programming language. Slightly more interesting might be a string that has like variables embedded in it. I'm thinking like the kind of string that you pass as the first argument to printf in C. Your document might have a bit more structure than just a string. It might have like formatting and bulleted lists and so on. So I'm thinking things like Markdown or HTML.
Did you have slides that you wanted to present but are not presenting? Okay, good.
You may also want to specify some computation that needs to be done in order to produce that document. So, for instance, you might write a for loop that generates the elements of your bulleted list. Anyway, this paper asks, what is the analog of the lambda calculus for document languages? Like, what is the essence of a document language? If you can come up with this, then this will enable careful reasoning about all of the subtleties involved in the semantics of such languages. And there are indeed many subtleties. Okay, paper 3, validating modern JSON schema. Okay, so this is about JSON. JSON is a widely used DSL for writing structured data. So it's made up, a JSON file is mainly made up of key-value pairs and arrays. And it's often used for sharing information between like web applications and that kind of thing. Now, if you want to communicate via JSON files, you're going to want to establish the format of those files. You're going to want to say what a file is expected to contain or not contain. And for this, you can use a JSON schema. So a JSON schema might say something like, your JSON file will have like the customer's first name, that will be a string, customer's surname, another string, and then an array of all of the shopping items in their basket. If you've got a JSON schema, you're going to want to be able to validate that any particular JSON file meets that schema, is a valid JSON file. And you're going to want that validation process to be efficient, because you're going to have to do that a lot. Now, the fiddle here is, well, the complexity here is that JSON changed a couple of years ago, and you've now got modern JSON. Now, when they did that, they added a few new features with complicated names like annotation-dependent validation and dynamic recursive references. This paper analyzes the impact of those new features. It gives them a formal semantics, and it also uses that formal semantics to analyze the complexity of this new validation process. Turns out it's rather more complex than it was before. Final paper then, paper 4, is called Shoggoth, and this is a paper about rewriting. So rewriting is a powerful and versatile method for expressing syntactic transformations. For instance, you can express computation. You can express the execution, for instance, of a lambda calculus process, beta reduction, and so on. You can also express compilation. You could use rewrite rules to show how a source program is successively rewritten into the target program. You could use rewriting to express proofs, say rewriting the left-hand side of an equation into eventually the right-hand side. Now, what you could do is just define a bunch of rewrite rules and then say, go ahead and rewrite if you can. But there are times when you want a bit more control over this rewriting process. So this brings us to strategic rewriting. And there are many DSLs, well, several DSLs, for expressing rewriting strategies. These strategies might say things like, do this rewrite rule and then do that one. Or try this rewrite rule. If that one fails, do this one instead. Or do a pre-order traversal of the AST and apply such and such a rewrite rule at each leaf. This paper asks, can we prove that a certain rewrite strategy on a certain set of rewrite rules is guaranteed to terminate? And if it does terminate, can we guarantee that when we end up with that final term, that term will satisfy some property that we want? So this paper, in summary, aims to provide the first rigorous treatment of strategic rewriting. And that would be the end of the session. Thank you.
Yeah, that concludes the preview session. These are previews for not the next session, but the one after that. So you can catch that at 10 to 5. And it's currently 3 minutes past 3, and the next session is at 10 past 3. So you got some time. Thanks for coming. Let's thank our speakers again.